Almost there, folks. And it's official. Welcome back. So we're finishing off week 5, but I just wanted to mention this looks like it's our first serious inclement weather day. So if you didn't make it today, but you came in through Zoom, good on you. That's always a good call. We might have some even worse severe weather, just depends on what's on the horizon. Also, for what we're doing today, we're going to go through section 8.1, potentially finish it quite early, but I didn't feel like it was a good idea to post the 8.2 notes just yet, since due to the inclement weather, I don't want to hold people on this campus for too long. So we're mainly going to go through section 8.1. Our goal is to find the arc length of random curves like this one, the arc length of a function y equals f of x from x equals a to x equals b. I'll just say L, saves a lot of oxygen that way. And this is the equation that we derived, but we didn't get a chance to actually use. So that's what we're going to be doing today. As far as the rest of the announcements, let's see here. I should have exams graded quite shortly once we get going onto the weekend. And for the people who took exams on a testing center, I'll be emailing them back to you. But out of the sense of fairness, if you did take the exam in class and you're just dying to know your results, send me an email over the weekend once you see your grades posted on Moodle, and I'm happy to scan it so you can take a look at the exam a little bit early before we come back on class, not next Monday, but next Wednesday due to the holiday. And I think that's my main announcement so far. Any questions or comments or things along those lines so far, folks? Okay, well, we're going to compute the arc length. We're also going to take another look into differentials and derive a arc length function or work with it. That's going to be a little bit weird at the end of the 8.1 notes, but the arc length function will come back again in section 8.2, and all the way back in chapter 10.2, it makes another comeback. And it's just one of those things where differentials are pretty weird, especially when you combine them with these kind of processes as well. So it's an early look into the kinds of stuff that comes up a lot into Calculus 3 as well. Other thing I put here on the notes, more just out of a sense of if you want a really good application of the arc length function, this would be one of them. I'm going to post the solutions to this, but if you would like to take a look at it, give it a try. I think it's a fun problem to try on your own. It looks like this. It's a pretty honest application. You can tell I lifted it out of a different textbook. That's not great graphics. But the idea is if you owned this property right here, there's certain things you're probably going to want to know about it right away. You're going to want to know the area of this property. Who knows what you're doing with it? If you're growing, say, rice, barley, something along those lines, you need to know that area. And in this property, it's demarcated by this road, but also by this stream that runs through the middle. There's coordinates given at several measurements along the stream. And so what you'd also want to know is, for this data right here, fit a function to it. It's asking for a degree 4 polynomial curve. Degree 3 is going to work as well. And then once we have that, we can find the area under this curve. We can also find the length of this curve, which would be the approximate length of the stream as well. So this is a very honest, it's a messy application, as most real world applications are. A good one to give a try. Again, I'll post the solutions to this one down below right here afterwards, but it's a fun one to give a try on your own as well. If we have a little bit of extra time, we might show how to start the regression process, but again, I don't want to keep people here too late tonight due to the weather. That's a lot of announcements so far, almost 4 minutes in, but here's where we left off. Right at the theorem telling us the arc length of a curve. The arc length could be described in this way. This is how we derived it. If prime comes into the picture, which is a surprise, and because it comes into the picture, that's the purpose of this assumption right here. Asserting that f prime must be continuous is just to allow a guarantee of integrability right here on the formula. Also, when we say that f prime is continuous on a closed interval, another way to say it is that your function or your curve is smooth. So we're looking into smooth curves in that kind of sense. Now, this is what we derived right here. But it turns out for the problems that we're going to be looking into, oftentimes this is a better way to look into it. With y equals f of x, Leibniz notation is a good call for these kinds of problems very often. We'll see why when we get into part B. But here's the first example to start us off. We want the exact length of this curve. And it's often, like with a lot of problems in calculus, really helpful if you can get just another way to visualize this. It gives great traction on your brain for everything that you're doing down here if you just have another way to visualize what's going on. So first thing we'll do is open up a graphing calculator. On exam questions, I often plot the curve on paper. Not that it's required to see the plot, but it can give you a reasonable estimate on if your answer is correct, if it's in the right ballpark, or if we're way off just by knowing what the curve is. So let's plug it in. Y equals x cubed thirds plus 1 over 4x. Domain condition is we're going from 1 less equals x, less or equals to 3. And this is the curve that we're trying to work with. So the way you could use this as a check is, if you grab that coordinate there, you can just use the equation from the distance between those 2 points. It's not the length of the curve, but the true length of the curve ought to be very close to that. So this is what we're working with. Next thing we're going to do is calculate the length exactly. And we'll show that check once, just in case that's a valuable thing to come back to in homework or exam settings. So there's lots going on with this theorem. You're integrating the square root of 1 plus a derivative, but the derivative is squared. The square root is a challenge here because we know, just based off section 7.3, sometimes when there's a square root in the integrand, it seems like a trigonometric substitution is our main objective. These problems aren't quite going to go that route, but still the struggle here algebraically is, how do you get rid of that root? Because so much is going on here algebraically. One strategy here is work inside out, think order of operations. Let's first just calculate dy dx. So back over here, the level of zoom makes these graphics kind of weird. There we go, that shows up the x better. I'm going to rewrite the function just to make it a little bit more susceptible to differentiation. It's 1/3 x cubed plus 1/4 x power negative 1. So if that's the function y, then dy dx would be equal to, just differentiate normally over here, we're going to get x squared minus 1/4 x power negative 2. So now we've got the derivative. Next thing we want to do is square that whole thing. So new comma, dy dx squared is our next thing to compute. So this would be the square of x squared minus 1 over 4x squared. All I've done here is taken the x power negative 2, and dropped it into the denominator. So we'll square all that, and we'll get, let's see here, x squared squared, so x power 4. When we FOIL and multiply here to here, we just get negative 1/4, and we get it twice. So negative 1/4 minus a 4 is a half. Then finally, last thing, this quantity squared, so that'll be plus 1 over 16 x power 4. So we've got the derivative squared. Now we're up to this part, 1 plus the derivative squared. And this is the critical part, because if our goal is to get rid of the square root, our goal is to take that whole thing and factor it so it's something squared or any even power so it can cancel with the root. So here's the big step. 1 plus dy dx squared. I should ask first, any questions to this line, getting the derivative squared? Okay, so now 1 plus the derivative squared doesn't seem like a big step, but it's kind of the biggest step on here. So 1 plus dy dx squared is just adding 1 to this whole thing. When you add 1 to it, that just becomes a positive 1/2. But let me write it in so we can just connect the dots. Okay, there it is written in. So now we can combine our constants, rewrite this as x power 4 plus 1/2 plus 1 over 16 x power 4. And for the next step, we're going to factor this equation. kind of a weird equation to factor, right? Especially with the order that it's written in, with a constant in the middle. But actually, that's exactly what we want, because we're going to factor it. Notice we kind of already have a hint. Go backwards from this line to this line. That's the factorization on this one. Only difference with the factorization on this one is positive sign right in the middle. So factoring this would give us x squared. Positive because of the positive and positive signs we see here. Square root of this portion is going to give us 1 over 4x squared. And now my claim is, if you FOIL that out, we're just going to give the line to the immediate left. So we did it, folks. We've done 1 plus dy dx squared. The next thing to do here is to square root it. This is the point where I would probably personally take this and drop it back into the integral. So this is the hard part, in my opinion, of arc length. A lot of these problems are very, very touchy algebraically, because antiderivatives are hard enough as it is, and especially if there's a square root in the mix. Any questions down to this line, getting the factoring going? Okay, for some reason, our author, in the actual problems in the textbook, this comes up a lot. I think that's because it's actually quite hard to come up with a random problem where this is an easy integral. So this is a very common thing that does come up in the homework as well. Weird factoring like this. Last thing we can now say is L for arc length is this definite integral, or just as good as this one if you prefer prime notation. We'll integrate from A to B. The A and B are just the bounds on x that gave us the curve. So we're integrating from 1 to x, or excuse me, 1 to 3 of the square root of 1 plus dy dx squared, which we found to be this. It doesn't hurt to leave that highlighting in. So x squared plus 1 over 4x squared. Squared goes in at that line. But at this point, we're home free. The square root cancels power 2. All we're now doing is integrating from 1 to 3 of what's inside the radicand, x squared, plus 1/4 x power -2, just a little bit better for me to visualize the integration, moving that one around. And now we're just smooth sailing. We're going to compute this out to get a value. And even though the check isn't required in homework, we'll show how the check goes to see just how close we are doing it exactly versus an approximation up here. Any last questions, folks, to this stage? Okay, next up is antiderivative. It's a third x cubed, then minus a fourth x power -1. We'll evaluate this all from 1 to 3. So this turns into, throw a 3 inside here, we have a third times 3 cubed, so that's just going to be a 9. And that x power -1, that's kind of a nuisance. Let me take one extra step. You know, taking this x squared and putting it up here, it helps with integration, but then it causes problems down here. So you have to decide at some point if you just rather integrate this in the normal way. But again, for me, visualizing it this way just makes sure we're really getting the right value here. The exponent went up by 1. But one last look at this. We're taking 1/3 x cubed minus 1 over 4x, evaluated to 1 to 3. And this just feels a little bit cleaner, plugging it into this form. So 1/3 3 cubed minus 1/12 with the upper limit of integration 3. Then do it again for 1. Don't forget the parentheses because of the 2 terms. It's a third minus a fourth. So we're getting there. Now we have just a little bit of arithmetic to get through. This is 9 minus a 12 minus a third minus a fourth is a 12. So this is minus a 12th again. So we have 9 minus 2/12, which means we have 9 minus 1/6. Almost there. Now, common denominator, these have a way of just keep on going and going. 9 with a denominator of 6 is 54/6 minus 1/6. So now we have an exact length. 53/6 is our claim for the exact length of this curve as it goes out from 1 to 3. Who knows if that's accurate or not, but we'll take another look at it by estimating the length just off this graph. Any questions first before the check on getting down to here? Okay, so we have an exact figure. Let me get some space going down here. And down below, we'll say that this is the check. In the check, we'll consider the graph, and I'll provide a graph like this on a real exam setting. That should be a good screenshot for us. Next thing we need to do is estimate coordinates. So this will be about at coordinate. It's just going to be an approximate check. So okay if you grab approximate coordinates. This is about 1, and let's say maybe 0.7. I'm doing the check as if we're doing it on a real exam setting where we can't necessarily go to Desmos and grab that value. It's closer to 0.5, 0.6 than a 0.7. Let's actually put it in the 0.6 just for a slightly more accurate value. Then up here, again, if we were doing this as an exam problem, we would just say 1, 2, 3, height 5, 6, 7, 8, 9. Looks like coordinate 3, 9 on that one. Just double checking. Yeah, just about. So the distance between those 2 points is going to be relative to this vertical line segment. This has length. Equals to the square root, difference in the x coordinates, so 3 minus 1 squared, plus the difference in the y coordinate squared, so 9 minus 0.6 squared. This is a good point to just throw it into a calculator because it's only just a check. We don't need to try to calculate that exactly. We have square root. This will just be a 4 plus, I'll put this one in, 9 minus 0.6 squared. We're told that it's about 0.86. So about 0.86 going this way. Now, once we have that figure, we go to our answer. And if we're off, way off, or hang on, I'm way off down here. 8.6 is what I should have put here. Our check is going to look really odd. 8.6 finally. Now go back to this 53/6, and we get 8.8. It should be bigger because this is the closest path, a direct line segment from point to point. We curved a little, so we added a little bit of distance. Again, that gives us really, really good numerical evidence we're on the right track. So that's a good check that you could have if you had extra time in an exam setting, or maybe just another look at a homework problem that you're working on to see if the number you got is even plausible. Well, any questions, folks, on the full process or the check? Okay, now we can compute lengths of curves. We'll do it all over again. So here's our part B down below. Notice the weirdness first on part B. It's a x equals a third root y minus 3 multiplied, meaning now this time y is the independent variable. Makes sense, we have bounds on y. X is the dependent variable. So this is an extra weird curve. But we can still find the length of it. Let's first just get a feel for what that curve looks like. X equals 1/3 square root y minus 3. There's our curve. Now, it's plotted it in an ordinary xy axis. So one thing to note right away in this curve, violates the vertical line test. Well, that's just because x is the dependent variable, not the independent variable. If you have an x equals and you want it to be a function, it has to satisfy a horizontal line test, which it does. But this failure right here on the vertical line test means it's not even actually a good idea to try to solve for y on this one. It'd be an awful slog anyways. But there are 2 functions that could describe this with y as the dependent variable. We'd have to sort out using the bounds which one is right to find the length. But here's an alternate strategy. The formula for the length of the curve is symmetric with x and y. What I mean by that is the length can either be described as integrate from a to b, root 1 plus dy dx squared dx, or if the situation calls for it, because our curve is just extra weird like this one, x is the dependent variable, just as good as a formula, length is integrate from a to b, root 1 plus dx dy squared dy. So what this is essentially saying is, if you have changed the roles of x and y entirely, no problem. Just change the roles of x and y in the entire formula for the arc length, and you're all set. dy is just our indication. The limits a and b are 1 to 9 now. Dx up here is telling us x is the dependent variable. We've solved for a function of x. Excuse me, we've solved for x as a function of y. And so this is just going to go in the same kind of way. This is why Leibniz notation is kind of preferable for these kinds of curves, because they are often, well, not often, they are sometimes specified in this weird way. Well, any questions, folks, with either the new formula or the situation before we give it a try? Okay, well, just like before, actually, let's put this on the next page just to kind of tie these concepts together better. Just like before in the last problem, good strategy is work this out first and then just plug it in. Not that you have to take that strategy. Plenty of people like copying down the whole thing. Not a problem if that's your preferred method. I do think it's a lot of extra writing. That's the only reason I'm going this different route. Step 1, just compute dx dy. That's a product rule, but it doesn't have to be. Maybe step 1 should be to sneak out of the product rule. Let's rewrite the function x. I mean, we did that on part A as well. We rewrote the function y just to make it more amenable for differentiation. Same thing here, x is 1/3. Y is to power 1/2. Y minus 3. This turns into 1/3. Distribute through, y power 1/2 times y to the power of 1, 2/2, gives us y to the power of 3/2. Distribute the whole thing over here and nothing big happens except we cancel the -3. So we get minus y power 1/2. So that's just an easier x to look at, in my opinion, for the purpose of dx dy differentiation. So next step, we compute dx dy. Normal derivative, just changed variables. 3/2 is going to come down, multiply the 1/3. Y is to now power 1/2, or you could put in square root y if you prefer. Over here, we get minus 1/2 times y to the power -1/2. And this deserves some cleanup, so let's go to another line. Dx dy is equal to 1/2 square root y. That comes from cancellation here and just changing it to a square root. Here's going to be minus 1/2. I'm going to drop this into the denominator. Now its power is positive 1/2, which means you could throw a square root there if you prefer, but y power 1/2 is just as good. So we got dx dy down. Next thing to do is just square that whole thing. So let's give this a little bit more space. Dx dy squared is the square of all this. Let me just write it in to make it slightly easier to visualize. 1/2 root y minus 1/2 root y squared. If you square all this out, first it's 1/2 root y times itself, giving us 1/4 y. Then when you multiply here to here, you might have a sense of deja vu. The root y's cancel. It's 1/2 times -1/2 for -1/4. But then you multiply this way again. It's -1/4 minus 1/4, which gives us -1/2 altogether when we FOIL out and combine the middle terms. Last thing to do is just square the final term. This will give us plus 1/4y. So again, this looks like deja vu. This happens and turns out quite a bit in the homework set. So I decided to copy in a couple problems where that happens as well. Part C, it goes differently. So it's not going to be the same kind of strategy. But if you look to what we did above on the notes, add one, make this positive 1/2 and factor, we're just copying in those exact steps. So here's the next part. For 1 plus dy dx squared, we get 1 plus all of this stuff right here, a fourth y, minus 1/2, plus 1 over 4y. Combine the constants, and we have positive 1/2 in the middle right here. So 1/4 y plus 1/2 plus 1 over 4y. And now this whole thing gets dropped up in here, which means we really want to factor it to simplify the root. And notice how weird that feels. You usually wouldn't think, oh, I need to factor this kind of equation. It's all because of the context. If we're doing arc length, sometimes the algebra is just weird and there's no getting out of it. If I were to factor this, a fourth would turn into a half. And the y at power 1, well, the powers always get divided in half. It'd be y power 1/2 or square root y. We get plus in the middle. Do the same thing over here. This turns into 2. Take the root of the y as well. So 1 over 2 root y. So that's our total expression altogether. Now we can work with that. Drop it up here in the root. And we should be able to navigate and find the actual arc length of that weird curve. And by the way, we weren't looking at the total curve. When we're looking at this graph, we were just expressing, it's good to leave x here as the dependent variable because there's lots to figure out if you solve for y. But on the domain from 1 less equals y, lesser equals to 9, this is the actual curve we're finding the arc length on, just that segment right there. So again, if you wanted to, you can find a ballpark estimate of that. But we'll go with our value here. We can skip the check. We don't have to do it each and every time. First, let me scroll up to this line. So the length is going to be the definite integral from a to b. These are now the a's and b's. So from 1 to 9, we're taking the square root of this part. So 1/2 root y plus, well, when we go to integrate this, we might find that this is actually more convenient, that root y, calling it a 1/2 y power negative 1/2 and all that squared. So what I did to this one right here was I took something that's in the denominator, that's really to power, I should circle this one, that's really y to power 1/2. I want to bring it up into the numerator for integration, so it became negative 1/2 altogether. So still the same thing. But now at this stage, we can finally get busy with the integration. And when you do these kind of problems, you'll notice that most of the work is algebra here, getting through all this stuff to get power 2. The actual integration is really pretty minimal in a lot of these problems. So now it's an integral from 1 to 9 of 1/2. And even this root y, let me re-express it as y power 1/2 plus 1/2 y power negative 1/2 dy. And we're off to the races on this. Let's get an antiderivative here. This is going to be 1/2 times, new exponent is 3/2, multiplied by its reciprocal 2/3, and then do it all over again. Copy in coefficient 1/2 here. Add 1, which is 2 over 2 to this, so it's 1/2 for the new exponent. So we multiply by the reciprocal 2. All that's evaluated from 1 to 9. But you never would really want to do the evaluation with it in this form. There's just too much noise going on. If we simplify, it's all a lot more accurate. So let's cancel the 2's over here. 1/3 y to 3/2. Over here, this is just plus root y. Evaluate that from 1 to 9, and we'll be home free. So First 9 gets dropped in right here. 1/3 times 9 power 3 halves plus 9 in here is just root 9, so 3. I'll write it in as a paper trail, root 9. Next, throwing 1s in, we get 1/3 plus the root of 1, which is just a 1. Almost there, we needed to figure out 9 power 3 halves. You know, that's good practice to compute this one by hand. Good practice with exponent laws. 9 power 3 halves becomes, I always put the numerator exponent as a far outer exponent, so the numbers don't get too big. This denominator becomes the square root. Usually we don't put the 2 in, but just to emphasize, that's where that would go. Then we're taking square root of 9, which is 3, and cubing it to get us a 27. So that whole thing, we're looking at a 27. So 1/3 times 27 plus 3 from over here minus 1/3 plus 3/3 gives us 4/3. So that means we're subtracting 4/3. Now it's just pure arithmetic at this point. 3 goes into 27 9 times, plus 3 for a 12. Minus 4/3 becomes 12 with a denominator of 3 is 36/3. Minus 4/3. Let me know if the numbers go weird. There's a lot of arithmetic at the end. Finally, we get 32/3. And that's a good stopping point. We have an exact figure. And now that is the exact length of this weird curve as y ranges from 1 to 9, or just more easily to visualize over here in this way. So 32/3, if you had to build a fence, you would know that you're going to need enough material to cover this kind of length. And you're also going to have some really great craftsmanship techniques to curve it in that kind of way as well. But any questions, folks, with that second look of arc length? Okay, these problems are both part A and part B really highly similar. The big part with part B was handling when X is the dependent variable, and also dealing with factoring on this step, which looks just extra weird going from here to here. But now when we go to part C, this one really is truly different. The algebra, we're going to start off in the same kind of way, but it does go a little bit differently. And I'm not sure why I say that. Let me close that there. We're not doing statistics. Let's take a look at the curve just like before. Let your subconscious chew on what you're about to do while you get a bigger look at the problem, is what we're trying to do. So here's natural log cosine x. That's a periodic function, so we couldn't find the arc length of this. There's vertical asymptotes everywhere, but you can on a finite domain. So let's go from 0 less than or equals to x, less than or equals to pi over 3. A curve disappeared. That's kind of concerning. Oh, thanks for spotting that. That's weird. Yeah, that was totally invisible to me. Curve is now, well, it's just that. There's our curve. You know, you can estimate the length of this pretty well, because if it went from here to here, well, that's just the diagonal of a unit square. The diagonal of a unit square is the square root of 2. So this is not the square root of 2, but our answer for the arc length of this should be pretty close. Let's give it a try. First, a good strategy here is write down the formula you're about to use. It'll force you to memorize it, which just means come time for the exam, even though this will be a provided formula, you'll be way accurate and better able to use it. So first step, length is going to be the integral from a to b. That's 0 to pi over 3 of the square root of 1 plus dy dx squared dx. So normal integral this time, if x is in the middle of these bounds, you expect to see a dx here, and now dy dx, which matches up with y being the dependent variable. And this is the first time we didn't have to do anything special to that function. We could just differentiate it right as it stands. So dy dx, you know, let me do a slightly different strategy. If you wanted to, If the Leibniz notation is just a little bit annoying, this is totally fine too. Let's go with the y prime just to express that's okay notation as well. To differentiate a logarithm, you get 1 over whatever the input happens to be, cosine x. Not the full story though, we have to multiply by something. Anyone spot what goes here? Absolutely, good call. We always have to look out for the chain rule. If the input is not x, I mean, even if it was x, x goes down to the denominator, and you do multiply by the derivative of x, it's just a 1. This time it's more spectacular. You multiply by the derivative of cosine x, negative sine x, as you said. So chain rule here. It's always good to be on the lookout for that because we're doing so much integration. Sometimes it's easy to get a little bit foggy on the differentiation. So negative sine over cosine is what we get. But this problem is really now a little bit more about reviewing trigonometry at this point. Sine over cosine is a tangent, so this is just a negative tangent x. So we've got the dy dx. Next thing we'll do is square that thing. So here's y prime squared. It goes nice. We're just taking negative tangent x, squaring it, and that gives us a tangent squared x. So we're on our way. Now we're ready for the full expression inside the square root. 1 plus dy dx squared is now 1 plus, well, just this, tangent squared x. And this is kind of concerning in a way, because if we put 1 plus tangent squared x here, fully accurate, but you cannot split a square root across plus. That's why we were working so hard on factoring these things. No way we could factor that. We need something else. You want to see what we should do? Good call. This is just a trigonometric identity, secant squared x. But that gives us exactly what we want. Secant squared is going to cancel with this square root right here. We want to be maybe a little bit careful. Secant squared, if it ever went negative, would imply that the square root of something squared is the absolute value of it. But on a domain from 0 to pi over 3, secant, which is the reciprocal of cosine, is in fact positive. So when we go to hit it with the square root, there will be no absolute value in this problem either. It's just a lot harder to see on this one, I think. So now we're ready for the arc length, L. Integrate from 0 to pi over 3, square root of secant squared x dx, which means we're just integrating from 0 to pi over 3, secant x dx. This is an antiderivative we've derived once and then never again. This is a given derivative at the end of the exams. But when you work with these over and over again, as a way of just sneaking into your brain, anyone remember how it goes? Good call, absolutely. Secant x plus tangent x. That's one of those antiderivatives that if I'm not teaching calculus 2, it's been maybe 6 months or a year, I start to forget that one. But in this class, we use it a lot. It just becomes part of what we're used to dealing with. Evaluate from 0 to pi over 3 on that, and we'll be on our way. Well, any questions so far, folks, to this stage? Oh, I'm just trying to zoom to a good spot. There we go. You know, before we start plugging in values, another good strategy here is let's just compute some of these trig functions. We are going to need let me use a different color pen here. We're going to need a secant at pi over 3. This is just the reciprocal of cosine at pi over 3. Cosine at pi over 3 takes on value of 1/2. So this is a reciprocal of 1/2 for just a value of 2 altogether. So we've got that portion taken care of. Next, evaluate tangent pi over 3. Tangent of pi over 3 gives us sine pi over 3. Divide by cosine pi over 3. Sine of pi over 3 is the square root 3 divided by 2. Cosine pi over 3, we've done once, and here it is twice. It's a half. Those halves cancel, and we just get root 3 altogether. Two more to go, almost there. Secant at 0. That's just 1 over cosine 0. Cosine 0 is 1, so we get 1 here. Finally, tangent 0. That's sine 0 over cosine 0. Cosine was 1 in the denominator, but sine is 0 in the numerator, so we just get 0 right here. So that's the grungy trigonometry scratch work. Keep in mind, on the back of every exam, you do get a trig table on the first coordinate that helps out with all this kind of stuff. But we have to know what a secant is, what a tangent is, to really use that table. But once we get here, we can now say arc length equals natural log, absolute value, secant at the pi over 3 came out as a 2. See the table below. Tangent at pi over 3 came out as plus root 3, so that's the first part, minus natural log absolute value of. Now we're plugging in the zeros. We got a 1 for secant, plus 0 for tangent, and this is then just the natural logarithm of positive 1. It goes to 0, so this is gone. That comes up a lot, it turns out. Natural log 1, natural log e just seems to be baked into a lot of questions. So our final expression for the arc length is natural log 2 plus root 3. I dropped absolute values just because of the positive quantity. And here, then, is the moment of truth. That expression is supposed to be the exact arc length of this curve. We approximate it pretty crudely by taking the diagonal, which is square root of 2. So this is how close we got. Natural log 2 plus square root 3 is very close. Notice it's smaller. That's because I went pretty far going in this direction. A more accurate check would have been from here to here instead. But it's just tempting to throw in the square root of 2 when you see it. So I would consider this excellent numerical evidence. That is indeed the right exact length. Well, any questions at all, folks, getting to that step? Okay. Well, these are the major things that we're going to be doing in the notes for the homework sets. There's still one kind of an annoying topic left over in this section, 8.1. It's annoying not because it's a bad topic, it's annoying because our author doesn't really support it with very many exercises. I think there's just one that's not very helpful. So it's not something I could really ask as a homework set or an exam question, but it is something that comes back in section 8.2, section 10.2, so we should consider it. We need to think about the fundamental theorem of calculus part 1. Then we'll look into the arc length function. Like I mentioned, I don't want to keep people too long today, so this will be our last concept for the night, looking into this. But first, before getting into the arc length function, we need to revisit once again fundamental theorem of calculus part 1. We've seen it in lots of different ways. It tells us if you have a continuous function on a closed domain, that automatically it's integrable, but in particular, you can define a new function g of x. It's an integral function that says, find the area under the curve of f of t from a point A up to x. So it's the area as you take x as a middle value between A and B, or the area so far function as x is in the middle. The major statement in the fundamental theorem of calculus part 1 is that's differentiable automatically, and the derivative of it is the integrand. F of t becomes f of x. And the explanation for t here is you can in fact write x. I've had some professors that did just that, didn't cause them any problems. It just caused a little bit of confusion in the classroom, because if you put x there and there, it's a conflict of notation with this x up here. So the only reason to change from x to t is to eliminate that conflict of notation. You have the right expression if you did put in x, it just looks pretty funny. So just to practice with the fundamental theorem of calculus part 1, here's a function g of x, which is an integral function. We can evaluate the derivative pretty much automatically. You go g prime of x equals, grab the integrand, but just convert the convert the variable, sorry, talking is getting hard, to x, 1 plus x cubed. We're done. That's a derivative. It's like the world's best derivative, except you'd have to know that it's through this. It makes it a trick problem, really. But what we're really interested in, the reason we're discussing the arc length function down below in the notes is it's more about the differential of the arc length function. So let's compute the differential of g as well. When you have a function indicated this way, the differential goes dg equals, then in the middle, it's g prime of x. We've already calculated it, so we'll go root 1 plus x cubed. That's not the full story, though. For the differential, there's a new expression over here. It matches whatever the variable is. It'll be a dx in this problem. So that's our differential, dg root 1 plus x cubed dx. It's really weird to explain what the role is of the differential. Calculus 1 attempts it back in the linearization chapter section. But the real purpose of the differential is it helps us to do expressions and integrals along the lines of u substitutions and other interesting stuff we're going to see. So once we have a differential, we can take the differential of this function as well. This is the so-called arc length function. And it's really bizarre in the sense that you wouldn't think that a function like this comes up a lot, but it does. It comes up in lots of surprising places. We expect to see it in the surface area problems, but it comes up again in chapter 10, which is surprising. So a visualization of what's going on here is we have a curve y equals f of x defined from a to b. So here's the a, here's the b, here's the function. But then we define a new function, an integral function, just like in the statement of the fundamental theorem of calculus, s of x integrates from a to x. This expression, that is the arc length expression. So the interpretation is, if you put a value inside here, x, call it x naught as our author does, put maybe an x naught here, then what Sx calculates is the arc length up of this portion here. That's kind of hard to express. Let me say it this way. So from here, Sx naught, down to here, is what's being calculated when we plug in a value. So it's giving us the arc length of this curve, or the arc length so far, as x naught moves all the way up to b. That's kind of a nice function because once you define it, you could calculate its derivative, you could calculate its differential. In calculating its derivative, you now have a rate of change. You can now talk about the speed at which this curve is being traced out. That's the connection in chapter 10 that we're going to take a look into. But what we want here to finalize the notes, and we'll come back here and use it when we have the opportunity to, is just the differential. So here's the big result, the reason why we looked into the fundamental theorem today. The differential of the arc length function, this thing here, is, we go back over here to start differentiating. Well, not differentiating, compute the differential, which means s converts into ds. We go over here. When we take the derivative of this whole function, which goes to this part of the differential, all we do is grab the integrand. So we take all of that right there, root 1 plus. We now convert back to the variable x. It was only t to avoid conflict in notation. So f prime at x squared. We finish off the differential by putting in whatever the variable is. If it was z, we put in a dz. It's x, so we put in a dx. So that's our whole differential. And notice what this implies. It also tells us, therefore, L, the arc length of the whole curve, is just integrate from a to b ds. And that is a literal way that sometimes the arc length function is defined, the length of a curve rather. just by putting in the differential and calling it good. Because that is the right stuff that goes in when you do the full substitution. But it has other purposes. We'll look into this quite a bit more when we get into section 8.2 and way down the line in chapter 8 when we're in warmer weather. But any last questions then, folks, with that last discussion here about that function or its differential? Okay, well, that's all I have for folks today. We're ending about 16 minutes early and a little bit of change, mainly because I'm now officially out of material, and also the roads are really bad. That's the other major reason. Again, if you're really curious about this problem, this is a great one to test your knowledge on what's really going on with arc length. This is that file right here. Give it a try. I'll have the solution posted before we come back on class on Wednesday next week. But have a great holiday, folks. Have a great weekend. See you all next time. And drive safe if you're driving.
Have a good night.
Thanks, you too.